differential privacy is a rigorous mathematical definition of privacy. In the simplest setting, consider an algorithm that analyzes a data set and computes statistics about it, such as the data's mean, variance, median, etc. Such an algorithm is said to be differentially private if by looking at the output, one cannot tell whether any individual data was included in the original data set or not. In other words, the guarantee of a differential private algorithm is that its behavior hardly changes when a single individual joins or leaves the data sets. And our ultimate goal for differential private method is to release statistical information without compromising the privacy of the individual respondents, as I just said before. Here's the general setting for the differential privacy. We initially only thought the terms of a non-interactive setting. We can see here that in which the curator computes and publishes some statistics and the data are not public, are not used further. Privacy concern may affect the precise answer released by the curator or even the set of the statistic released. Note that because of the data, since the data will never be used again, once the statistics have been published using the non-interactive settings, the whole data sets will be destroyed. Alternatively, there is a second setting we call interactive settings, in which the curator sits between the users and this database. Query posted by the users and the response to these queries may be modified by the curator in order to protect the privacy of the respondents. The difference between the interactive setting and the non-interactive setting is that interactive settings, the data sets must remain, and the curator must remain presented throughout the lifetime of the database. Intuitively, however, you can see that interactive curator may be able to provide better accuracy since they only need to answer the question actually of interest rather than to provide the answers to all possible questions. And I'll also address the use of the differential privacy in real life. So the simplest and most well-studied scenario is statistic query release. A data owner can specify counting queries such as how many people in this data set are males, or how many people in this data set are from Massachusetts, for example, and receive answer perturbed by a small amount of random noises. Differential private algorithms are able to answer a large number of such queries approximately, so that a researcher sees these approximate answers can draw roughly the same conclusion as if she had the data set herself. So next, my teammate will talk about the algorithm behind.
So let's talk about the algorithm. The privacy. How we can preserve the privacy? We just need to find a random function k. What does it mean by randomized? It just means you can think it as we simply add some noise to the data set so that we can preserve the privacy. So our goal is to find a k, a function k, and this function will call the epsilon differential privacy if we put the data set D1 and D2 into the k, then the k will output another two data set, KD1, KD2. And this KD1, KD2 need to satisfy this equation. Sorry, this inequality. If this probability is smaller than this probability times this kind of thing, then we say this is very safe. So let's talk about what does this mean. You can think it, if you recall the decision tree, the probability is linked to the entropy, right? What does entropy mean? Entropy is the information. So if this inequality is satisfied, the k will increase the probability. So this two data set, the information given by this two data set will be different. If you set epsilon very large, then the difference between these two probabilities is very large. So we can we can find some interesting thing if we have two different data. For example, if I was in D1 and I'm not in D2, but these two show some very different probability, then someone will find some interesting information about me. But if these two probability leaks very little difference, then someone will not even know whether I'm in data D1 or D2. So that's the idea of the privacy. This is the equation derived by statisticians because I will talk about the reason later. Let's first look at the epsilon. Epsilon is the tuning parameter you can play with. If the epsilon decreases, the privacy will increase. If the epsilon is a positive number, if epsilon goes to 0, then these two probability will almost the same. If this two probability is almost the same, then we say this is very high privacy. Why? Because these two events leaks the same information, the same entropy. So K, previously I said we put a data set into K and I add some noise in, and the K will output a safe data set. Actually, K can be any function. For example, you can define K as the average. So if K is the average, you add a noise onto the average. So the average will be the same. For example, if I say, what is the average height in this class, and delete myself out of this class, what is the average then? This is D1, D2. From these two data sets, I can find the height of myself. This is very safe. This is something privacy. But if I add a noise there, you cannot say what is the height of me. And K can be also any function like this. And I say the K needs noise. So what is the noise will be? The first thing we need to look at is the sensitivity of K. Sensitivity of K is if D1 and D2 only differ at one element. For example, this whole class without me and this whole class with me. This is two different data sets except only me. And we calculate the maximum difference from these two data sets in K, and we name it as the sensitive. Then the noise will become the Laplace. We add a Laplace distribution with the parameter with sensitive divided by the epsilon. Why we define the noise like this? I don't know. but the paper said this process is non-invertible, so it's very safe. If this can invertible, then it's not safe, right? And this is a asymptotic efficient. What does it mean by efficient? Asymptotic efficient. This is because by some kind of large sample property and some central limited theorem, you can still have the same statistical property. For example, if the data set is large enough, the average height will not change with or without me. It's the same, right? So if the data set is large enough, this noise can guarantee that you still have the same statistical property. Your algorithm will be almost the same. Actually, there are some other noise you can add, like exponential and normal, but this is the most common one. Yeah, that's it. Differential privacy is very simple. You just add this into your data set, then everything's safe. Yeah, actually this idea is very simple, and it emerged a long time ago. But until recently, it has been proved it can inherit your statistical property. Sorry. Okay, let's look at some code. I think from my
my teammates' discussion, you have already realized the importance of privacy. So, given the data set, how do we productize it? I will introduce to you our package called Differential, which can make this super easy. There are two examples I will cover today. The first, we use the Laplace methodology, which is discussed by my teammate previously. The second one, we go further. We use the explanation mechanism with a little bit, a weakened version of the different privacy called the random differential privacy. Let's start with the first example. Here, the data set is, you can see here, the data set is basically 100 entries, and each entry is a real number lying between 0 and 1. Suppose this is sensitive data. And the first thing is that you need to import a library, of course. And the function, the target function here is mean, meaning that we want to release the mean of the data set to the public. And we want to make sure that the public cannot reconstruct our original data. So what can we do? This is the data set. First, we need to, using this library, we need to first define a mechanism. Here you can see we use the Laplace method. And the target is the mean, or the f defined above. The sensitivity here is 1 over n because if you have another data set that only differs 1 entry from the data set here, so the mean would differ at most 1 over n. And here I just set the privacy budget or epsilon to be 1, or you can change it to any positive real number you like. And the only thing remaining will be pass the mechanism and the private budget to the release response, and you will get the result. This is just the occur to get the result print out. So here, the original